Okay, so to save time, I had written a program last time, and I just reused this program. So we're going to do 100,000 trials, and we're going to count how long it takes to end, and sort of what the B is going to be the average it took for every trial.
Okay.
Okay, so I've got a bunch of variables in here. Each trial we're going to do 10,000 rolls of the 120-sided dice, just to make sure that we eventually do, we get a pretty good sample every time. Each one of those 10,000 trials, we're going to roll the dice up to a maximum of 10,000 times. But probably it's not going to be anywhere near that, since we have to stop every time we see an odd number.
Yeah.
So we're not going to go 10,000 rolls without seeing an odd number. But anyway, so if it's a 6, we say, hey, it took J steps, and then we exit out of the loop. If it's an odd number, we exit out of the loop.
Well, were we counting the 6 and the odd numbers as both a success?
We could do it either way. And this is the old way for the simulation, so where I just have 6 being a success. And then we see, here's what I got when we did this for our 120-sided dice. I forgot to show you. I was picking a number from 1 to 120. Okay.
All right.
So here's our histogram of the average number of trial times it took across our 100,000 simulations. So what would you say about this?
It sort of looks like a normal distribution.
It seems to be centered, kind of in the middle, and then drops off pretty steeply.
Okay. This is the actual number of successful times out of the 10,000 rolls we were doing each trial. So you can see we're not getting a lot of successes, right?
Yeah.
Out of 10,000, we have only 100.
Yeah, well, because now why is that? Why do we not get very many successes?
Well,
Why are we always having to start over?
Well,
the
because
probability of rolling a 6 is much lower than the probability of rolling an odd number.
That's right. So our 120-sided dice, it's just the probability of rolling a 6 is really low. So that's why we have to do a lot. So then I'm going to scroll down to a different graph I made. So there's a weird surprise in this graph. Let me shrink this. There's a weird hole right around 2.
the bottom of the graph isn't on screen.
Oh, that's all right. Well, I'll make it smaller. 125.
Yeah, there you go.
So I don't understand why
Seems like the other.
exactly 2 rolls as the average. But that's the average out of, on average we were seeing 160 successes, right?
Yeah.
So it's still a fairly big average. I don't know why that's...
It looks like the other one. The things around it are built up.
Yeah, either a weird rounding situation, or maybe I have to do maybe 10,000 trials. Maybe I need to make this 100,000. So I don't know. But anyway, I forgot to check to compare what our average was, 1.9663, to what 120 over 61 is, 1.96721.
Rather close.
So what do you think?
Well, it seems like this new way of thinking about it also, it's simpler to do. Like the program will be simpler and it produces the same result.
It seems like you can kind of just do it in your head, basically, if you know the geometric series is.
Yeah, it's a neat formula, and the formula that we ended up finding essentially shows that if you have no matter how big your die is, the upper limit is 2 rolls on average. You'll never get a situation that goes above 2 rolls.
It's just like, I think for an n-sided dice, and the expected number of rolls is n over like the number, and then n over 2 plus 1.
That's right.
It's the number of.
Very good. As long as n is
yeah.
even.
Mhm.
Yeah, that's right. Good job, huh? So I wanted to show this, the whole point of this project was to show a very advanced and sophisticated way of thinking about this dice problem that turns out to simplify it tremendously. And it's really cool. It's nice to have ideas like this in your arsenal.
Okay.
All right. Good work this morning, guys.